All right, good morning, everyone, and welcome back to Semel Grand Rounds. Today we have our very own Dr. Jonathan Flint here to give us a talk. If you have questions for Dr. Flint, go ahead and submit them at any point using the Q&A button. And don't forget to fill out the Qualtrics survey after the talk is over in order to claim your CME credit. And with that, I will turn it over to Dr. Gitlin to introduce the speaker.
Thank you, Jonathan. It is my pleasure to introduce Professor Jonathan Flint, who is our Grand Round speaker today. Since 2015, Dr. Flint has been the Billy and Audrey Wilder Professor of Psychiatry and Neuroscience at UCLA. Prior to arriving at UCLA, he was a professor of neuroscience and a fellow of the Merton University of Oxford University. Although Jonathan's overarching interest is understanding how genetic variation contributes to disease susceptibility, more recently, his main focus has been on the genetics of depression, on which he is arguably the world's expert. Over the last 5 years, he completed the largest project anywhere in the world in the genetics of major depression, collaborating with 60 hospitals across China and recruiting 6,000 cases and 6,000 controls with complete genomic sequences. Jonathan's CV is too overwhelming to quote from, given the incredible numbers of grants and publications he has received and published. Aside from his innumerable papers, he has also first authored 2 editions of a remarkable textbook entitled How Genes Influence Behavior. I recently read the 2nd edition, which was published a year and a half ago in 2019. It is a superb, casually written, but comprehensive review of genetic research in general, and specifically the genetics of psychiatric disorders and traits. I even understood some of it. I highly recommend it to those interested. Of note, Jonathan was a clinician for many years in the NHS in the UK before evolving into being exclusively a scientist. Of greater note, in 2019, Jonathan was elected as a Fellow of the Royal Society, the equivalent of our National Academy of Science, but of course, hundreds and hundreds of years older. The society was founded in the 1660s and has 16 or so alive members. Other members of society includes the likes of such as Isaac Newton, Charles Darwin, and Stephen Hawking. I think it is fabulous that only at a place like UCLA can we have an endowed professorship named for one of the great writer-directors in movie history, Billy Wilder, bestowed upon a faculty member with societal links to Isaac Newton and Charles Darwin. How cool is that? Since he has joined UCLA, Jonathan has become a very close friend of mine and my wife, Jeannie, and I can testify that among other wonderful traits, he makes spectacular bread from scratch and has the passionate love of Los Angeles that only those not born here, like me, have. Over the last number of years, I've asked Jonathan to give a yearly lecture in the Mood Clinic on understanding data and statistics. It is always a revelation, and we've asked him to provide a similar lecture today. It is entitled, How to Determine Whether a Claim in Psychiatric Genetics is True or Not. It is my great honor and pleasure to introduce Professor Jonathan Flint.
Thank you, Michael, for that very kind introduction. I am going to give you, in a sense, a sort of broader overview of how we assess the validity of findings, whether they're psychiatric or not. And in order to do that, I am going to give you, I will start with a little bit of history as to why I got involved in trying to understand the reason for this question. And then we'll move on to the meat of the talk. So let me start by introducing my friend. This is Marcus Manoffo, who is a psychologist now in Bristol. And Marcus and I used to meet for coffee regularly and discuss the state of psychiatric genetics and shake our heads in despair. Because at the time we were doing this, which was in the early 1990s, there were a flood of papers coming out, all claiming things like dopamine transporters or DRD2 receptor or the serotonin transporter were involved in common psychiatric conditions, schizophrenia, depression, and so on. And what we noticed was that the literature was very mixed. There were large numbers of papers reporting that there was some association and equally large number of papers reporting that they couldn't find an association. So Marcus and I embarked on an attempt to rectify this, and we applied, and I think we were probably one of the first to do this, a technique called meta-analysis, which is a way of combining data from different papers and trying to arrive at a consensus. And I'll just talk you through very briefly one example. And the example I'm going to choose is from this paper here. And I put at the bottom of this slide the number of times this paper has been cited, which is now, and will be, I think, certainly next year, almost 10,000. Now, to put that in the context, if you have a paper that's cited 100 times, you're doing really, really well. I mean, most of papers, I think the median numbers of citations is something like 2 or 3. 10,000 is spectacular. And the reason that this paper has attracted so much attention is summarized, I think, best in this figure. So what you're looking at here on the vertical axis is the likelihood of developing an episode of major depression. And on the horizontal axis are 3 categories of stressful life event. This is occurring in childhood. So if you had no maltreatment, maybe severely maltreated, or somewhere in the middle. And then you'll see that there are 3 lines marked SS, SL, and LL. And those are for 3 genotypes of the serotonin transporter. And a genetic effect is indicated when those 3 genotypes are distinct. And you can see that's the case in severe maltreatment. But on the left-hand side, where there's no environmental effect, the 3 lines coalesce, indicating that there is no genetic effect. And this is a classic demonstration of what's called a gene by environment interaction. That's to say that a genetic effect is only manifest under certain environmental conditions. And that beautiful demonstration attracted a huge amount of interest, and it followed very much the same pattern that Marcus and I have been discussing, namely that many papers found this and many papers didn't find it. And when we looked at this in detail, this is about 5 years later after the first publication, there were 33 of these studies. And we decided to apply our meta-analytic approach to this. And I'll show you roughly what that consists of. So in a meta-analysis, you do something like the following. You list all the studies listed on the left there, and then you work out the effect that they are attributing to the locus, or it could be an intervention, a treatment, whatever you're examining. And you represent that by a little vertical tick, which I think you should be able to see in the middle of those horizontal bars. And the horizontal bars represent the strength of the association. So whether it's I'll just 1 second. So a wide bar would be a very broad estimate, and a narrow bar would be a tight estimate. And then once you've got it into that format, you can simply sum up those things, and that will give you an overall estimate of what the effect is. And then you should be able to work out whether there's a significant effect or not. So that, in brief, is how that's done. So we published this report in 2009, and I've summarized here what we found. No evidence of significant between study heterogeneity, indicating it's probably a reasonable summary. No evidence of a significant gene by environment interaction. Now, this paper got a considerable amount of interest, as we were not the only group that had done this. Neil Risch, a geneticist in San Francisco, had done much the same thing. We both came to the same conclusion, that there wasn't an effect. And there was a paper in Science, a letter whose summary tells you basically how significant this was being taken back to the drawing board for psychiatric genetics. And I received hate mail over this. I mean, there was endless sort of complaints that we hadn't done it right and so on. And this story grumbled on. And I chased it up, and even a few years ago, there were still being papers about this. So this is from 2017, a collaborative meta-analysis, and again, finding no evidence of a strong interaction between that locus and the development of depression. So it's been an ongoing story, and I think this really emphasizes the difficulties of trying to establish whether we're seeing a true effect or not. Now, my colleague Marcus decided that we should take this even further and try and understand whether the problems were inherent in the entire field. And working with a number of other people, we managed to discover that one of the major things that's important here has been the size of the studies that were being involved. So I want to show you just one key result from this paper, which was published now in about 7 years ago. And what we've done is we've carried out a meta-analysis, not just of the genetic association literature, but really a broad range of neuroscience. And we were just asking the question, could we really assure ourselves that the findings that were coming out were robust? And the short answer to that question, unfortunately, was no. And let me show you the figure that backs up that claim. So here I'm showing you the power from 49 meta-analysis. So these are not this is not 49 single studies. We've actually taken 49 separate meta-analyses and looked across all of those. And the horizontal axis is the power that we're attributing to each of those meta-analyses. What we'd expect in a standard sort of grant application type way is that most studies should have a power of greater than 80%. In fact, a mere 15% of all of the ones we looked at had such a power. And a massive 30% had power of less than 10%. So this was a real wake-up call. And a large number of people have looked at this and wondered whether we were doing things correctly or not. One of the authors on this paper is Brian Nosek. And Brian Nosek, partly as a consequence of this, set up something called the Open Science Collaboration. And he decided what he would do is just test the reproducibility of psychological science by taking more or less at random 100 studies from the literature and getting collaborators to try and replicate those studies. And let me show you what he found. So this is an analysis of the 100 studies. And if you just start at the left-hand side where it says replications, p less than 0.05 in the original direction, there's 97 studies. So just look at the top line here, it says overall. So 35 of 100, that's 36%, he was able to say, yes, we could replicate in the same direction at the same level of significance. So just as a sort of ballpark figure, he's saying something like only a third of all the studies that he looked at, all 100, we assume they're representative in psychology, could actually be replicated. And to put that another way, here's a graphical representation. So rather than looking at the p-value, we're now going to look at the effect size. It's the extent to which the intervention, the genetic association, whatever it is that's been studied, and some measure of the effect. And on the horizontal axis is the published, the original effect size. And the vertical axis is the replication effect size, the ones that were found from the 100. The green dots means it's significant and the red dots are non-significant. And what we'd expect to find, which is where most of the green dots lies, they fall along this diagonal. So they're sort of roughly commensurate. But as you can see, as you'd expect, about 2/3 of these do not lie on that line, and some indeed are actually negative. So the direction of the effect is going in completely the opposite direction. So these two papers have really been a sort of thorn in the side of people trying to claim that their findings are correct or not. And it raised for me the more general question is like, how do we really know when we found something? How trustworthy is it? How can we be certain that what we've discovered is true or not? So for the rest of my talk, I'm going to go through a way of thinking about that problem, and I'm going to pose it in terms of the following questions. So firstly, when I look at my finding, I ask, have I used the right test? The second question I'm going to ask is, was the correct significance threshold applied? Then I'm going to ask a question about power. Did the experiment have sufficient power to deliver the result that was reported? And finally, was the p-value correctly interpreted? Now, I'll give you fair warning here of two things. The first is that the complexity of what we're considering increases as we go down the list. Dealing with the first question is quite straightforward, whereas as you'll see when we get to the last question, it's really very challenging. And the second thing I'm going to warn you about is that I'm afraid to say we're going to have a bit of audience participation. So just be warned when I get to that stage, because it'd be useful if you at least, if you don't have pen and paper, at least prepare to think through some of the questions that I'm going to show you, because I think that'll be useful for us all if we can tackle this. So let's start. So was the right test used? So as I've said, this is pretty straightforward. It's a technical issue. I'm just going to give you one example of how important that might be, and I'll do so with an example from genetics, but you can choose many from your own discipline if genetics is not to your taste. So here are some data from a study of personality. On the top here, we're seeing the 5 categories from the Ocean Inventory of Personality: neuroticism, extroversion, openness, and agreeableness, and conscientiousness. And the investigators who've done this study are looking for a genetic effect. You'll recognize the LL, the LS, and the SS on the left-hand side as the genotypes I described before from the serotonin transporter. So the 3 genotypes. And what we want to know is, is there an association between those genotypes and these 5 measures of personality? Now, what the investigators in this paper decided to do to test that hypothesis was firstly to categorize the genotypes in the following way. They broke them up into 2 classes. They said there was an LL group here, and then they said there was an S group here. So the group S and the group L. And that is simply by summing the LS and the SS to produce this group. And then they've got a simple comparison between the 57.4 in this column here and the 53.4 in here. And you've got the standard deviations to go with that. So that means their test simply becomes a comparison of means, a t-test, and they carry that t-test out, and it's a p-value of 0.02. It's less than 0.05, and they're very happy they can publish a paper. But is that the right test to do? Well, the justification is pretty meager, to be honest. I mean, why would they want to do that? It makes it simpler for them. We really need to take into account there might be variation between these genotypes as well. So this isn't necessarily the best test at all. In fact, we need to test the differences across all of those categories, and that would be an analysis of variance. And if you carry that out with the same data set, now you find that you have a p-value of 0.12, and that's not publishable. So the choice of test can make a big difference to whether you can get your significant result or not. So just bear that in mind. But this is usually a technical issue which you can resolve by speaking to a statistician. It doesn't require a lot of thought to get that one realized. Let's move on to my second question. Was the correct significance threshold applied? Well, I'm afraid to say that here things do become a little more taxing. The major problem here is what is often referred to as p-hacking. And the simplest way to think about p-hacking is that if we go out for dinner and I have a bet with you and I say, look, I'll pay for dinner by tossing this coin. If it's heads, you pay, and if it's tails, I pay. I toss the coin, it's a tails, and I say, oh, I think I should toss it again. I'll do it a couple more times. No doubt you will complain. I really should only get one chance at the tossing of the coin. Unfortunately, many scientific papers are not quite so fair in this respect, and they will do multiple tests, each time pulling out those which are less than 0.05. And there's a standard way of dealing with this, which is to divide the p-value, 0.05 that is, by the number of tests that you do and report only those which are below that significance threshold. So if you do 10 tests of your data, it should be 0.05 divided by 10, which will give you a threshold of 0.005 rather than 0.05. So we know about that approach and that problem. I think that's fairly well understood. But there are other issues which go a little deeper, and I would like to introduce you to this paper, this problem here, which is given, I think, most clearly by this particular story. I'm currently a PhD student in the social sciences department at the university. I recently got involved with a group of professors working on a project which involves some costly data collection. None of them have any real statistical prowess, so they came to me to form their analysis, which I'm happy to do. The problem, they want me to p-hack it, and they don't even know it. The professors want to send their project to a high-impact journal. They said Nature, Science, or The Lancet were the first three. There's no research question, very little underlying theory. They essentially dumped the data on me and told me to email them when you find something significant. The worst part is there's no malicious intent here, and I don't think they even know they're just fishing for p less than 0.05. These are genuinely good, smart people who just want to do a good study and get some recognition. I don't know if you have any advice to handling this sort of situation. So I wonder how we might help this student. Well, let's turn, first of all, to some authors who have considered this problem in I think, a useful paper on dealing with what these people have called the researcher degree of freedom. So this is an interesting way of generating significant results. And I think, again, as that story I've just given you illustrates, not for any malicious intent, really because people hadn't thought through some of the key issues. And let me just give you two examples of the way the thinking might work. So this might be a simple starting point. When you set up your experiment and you decide, I can stop collecting data when either statistical significance is less than p 0.05, or the number of observations in each condition is 50 or some other number that I have decided upon. That seems on the face of it a fairly reasonable starting point, and many people have taken that view. But if we check this in a little more detail, we find it's not quite as simple as we might expect. So let's take a figure from the paper I've just shown you and show you what I mean. So here you're seeing, this is simulations. We can argue with that later, but let's assume they've got the simulations right. And what you're seeing on the vertical axis is the percentage of false positive results. And they're showing two conditions, one when you start off with a sample size of 10, and another in the gray line where you start off with a sample size of 20. And what we're going to do is we're going to test. We're going to run another sample, add one on, and then test. And that's what the one on the horizontal axis means. Or we can add on 5 and then test the total. And that's what the 5 means on the horizontal axis, and so on. And those percentages written there are the percentages of false positive results if you follow each of those strategies. Or to summarize, a researcher who starts with 10 observations per condition and then tests for significance after every new observation finds a false positive result almost 1/4 of the time. So that is not a good strategy, despite the fact that I think most of us might have thought that was a reasonable way to go. It's that's not going to work. So that's one problem with the researcher degrees of freedom. Let me illustrate the second one. And again, we'll just start with I think a pretty simple observation. If an effect is significant with a small sample size, it will be significant with a larger one. So I'll run a study with 10 people. I'll get a p-value which is less than 0.05. Well, I think that's reasonable because, if I'd done it with 100, it would have just reinforced that result. So a small sample is perfectly okay if I get a significant result. Is that justified? Unfortunately not. And again, I'll turn to the paper for one simulation which will show you this. So what you're looking at here on the vertical axis is the p-value. The dotted red line is marking the significance of less than 0.05. And the horizontal axis is the sample size. So I start off with a small sample size, I increase it, and around about 20, 25, I see a significant result. But actually, if I continue to increase the sample size, there's no guarantee that that p-value will be maintained. So it is not true that if an effect is significant with a small sample size, it necessarily will be significant with a larger one. And understanding why that is the case brings us to the next question that I think we should be asking about our result. And that question is, did the experiment have sufficient power to deliver the result reported? A lot of people, me included, before I started thinking about this, would probably have agreed with this statement. I don't always do a power analysis, but when I do, I collect my data first. Not such a good strategy. Or to put it another way, I've just carried out a study. I've got a result that exceeds 5% significance threshold when I followed Dr. Flint's suggestions. I used the right test. I applied the correct significance threshold. I can publish my paper. Why do I need to worry about a power analysis? Well, let me, in the next 4 slides, just show you that you really, really do need to consider the power analysis. I'm going to take my example from a paper by George Davies Smith. This was published a few years ago now. Unfortunately, it's just as relevant today as it was 20 years ago. And what George does is he thinks up a situation. And the situation is that for good or bad reasons, there's a problem in the field that we're working in, whatever field it could be. In my case, genetic testing, it could be psychological testing, whatever we're looking at, doesn't matter. There's a problem in the sense that there's a proportion of findings in the field which we think are incorrect, they're false positive. So let's say that 90% of the published findings are wrong. I'm choosing 90%, as George did, really for illustrative purposes. It makes the math a bit easier, and you can see the results very, very clearly. That means that out of 1,000 experiments, there are only 100 true findings. So that's just restating the fact that 10% are true. And I've illustrated this in this table here, which is the one that is published in Davies Smith's paper. So what we're going to do now is we're going to fill in the other blanks in this table. And we're going to start by considering the second column, the true association column. So we want to know those which found something and those which didn't. So we have to assume a power. So let's make a guess at the power. We'll say, for argument's sake, that it's 50%. And if the power is 50%, it would mean that out of the 100 true studies, we would have missed half of them. So 50 we would have found, because we've got power to detect half, and 50 we wouldn't have found. Now we have that column in place, we can work along the next one, which is the no association. So we've got 900 where we have no association, and we're applying a 5% significance threshold. So by chance, 5% of those will be significant, which means that we'll have 45 which are less than 0.05 and 855 which are not. Now, the next slide is the critical one. So we can sum up along the horizontal, and we've got 90 studies out of 1,000 which have a p-value less than 0.05. And 45 of those, as we've just established, are not true. So that means that in this circumstance, only half the findings with a p-value less than 0.05 are true associations. That, I think most of you would agree, is not what we imagine that a p-value of less than 0.05 means. But when I say that, of course, it raises a really ugly question, which is, well, what does a p-value of less than 0.05 mean? And that brings me to the last, and I'm afraid the most demanding of the questions that I have to apply. Was the p-value correctly interpreted? So I'll go through this in detail, and I'll start again really with an anecdote just to illustrate the problems that we've got here. And this anecdote comes from the physicist Richard Feynman. So this man had designed an experiment which would show something which I do not remember. If the rats always went to the right, let's say, I can't remember exactly. He had to do a great number of tests because, of course, they could go to the right accidentally. So to get it down to 1 in 20 by odds, he had to do a number of them. And it's hard to do. And he did this number. Then he found that it didn't work. They went to the right, they went to the left, and so on. And then he noticed, most remarkably, that they alternated, first right, then left, then right, then left. And he ran to me and he said, calculate the probability for me that they should alternate so that I can see if it is less than 1 in 20. And I said, it probably is less than 1 in 20, but it doesn't count. He said, why? I said, because it doesn't make any sense to calculate after the event. You see, you found the peculiarity, and so you selected the peculiar case. So this is an illustration of how we need to establish the experimental design and test it appropriately. So let's move on now to see how this translates into the case where we've run an experiment and we've got a p-value. And I'll start with what I think is where most of us begin, which is the significance of a significance threshold of 5%. And even if we didn't know where this comes from, I've given the answer here. This is from Ronald Fisher from a paper in 1925. And Fisher argued that if a p-value is between 0.1 and 0.9, there is no reason to suspect the hypothesis tested. In other words, we wouldn't want to reject our null hypothesis. If it's below 0.02, it's strongly indicated that the hypothesis fails to account for the whole of the facts. We shall not often be astray if we draw a conventional line at 0.05. So that's, I think, most people's sort of general understanding what a 5% significance threshold is. The trouble which has dogged the field is, well, what if it's 0.06? What if it's 0.07? And how can we interpret something like, you know, how serious should we be about 0.05? And do we chuck things out? Do we include them? It's all sort of messy if you begin to press it. And the statisticians and the mathematicians took a sort of serious, hard look at this. And we have to thank Neyman and Pearson for bringing forward what they called null hypothesis significance testing, which was to take this rather poorly formulated view that we could draw a line at 0.05 and throw away the null hypothesis, and to make a much clearer and well formulated description of what the p-value was. And the p-value, now we're not talking about an exact 0.05, they're saying the p-value is the probability of the observed data or of more extreme data points, given that the null hypothesis is true. So a few words, but a really difficult concept to get across. And what I'm going to do in the next few slides is just to see some of the implications of that and maybe suggest some alternatives of how to think about this. But let's just deal firstly with the difficulty of that concept. And I'll do so with a paper published in 2002, which is written by two psychologists who wanted to know how well their colleagues, their students, indeed their own mentors, understood significance thresholds. And to do that, they took a number of studies and came up with some questions about the interpretation of those studies and presented those to their colleagues. I'll give you the experimental design. We asked participants from psychology departments to fill out a short questionnaire. We sorted those into three groups: methodology instructors, who are university teachers who taught psychology students about non-hypothesis significant testing. These include professors, some of whom are advanced students and so on. There was a group of scientific psychologists, professors and other scientific staff, and the last group consisted of psychology students. So altogether about 100 people. And what I'm going to show you next is the questionnaire that they gave. And I've already warned you what's coming, because I'm going to ask you guys to at least think about these questions. So this is exactly what they asked. It's a little long and maybe the text is too small, so I've simplified it just a little bit. So work from my version here, and I put a few little pointers in here about this. So you compare the means of your control and experimental groups, and you have a result of p equals 0.01. Your task over the next couple of minutes is to read the statements below and then decide whether they're true or false. So I'll give that, we're running about on time, so I'll give you maybe a minute just to read those through and decide for yourself whether you think it's correct or not. Okay, 5 more seconds. Okay, let's open up the box and see what's there. So this is the results from that paper. The questions are summarized here. H0 is the null hypothesis. H1 is the hypothesis you're interested in. So, for example, for my case, this will be H0, there's no genetic association. H1 is there is a genetic association. There is the six questions, and then there are the groups of people he asks. And over here, note there's another group. These are academic psychologists asked actually the same questions by another investigator 15 years before this paper. And one of the interesting things about this paper was that the 2000 paper was that they were seeing if the earlier results had changed at all. And as you'll see in a moment, they hadn't. So let's see what the investigators found. So that's the table filled out. Those are the people who thought those results were true. These questions were true. So you can see that the bulk of people thought that number 5 was true. Not so many people thought that number 1 was true, and so on. And what is the correct answer? Well, actually, the correct answer is that none of the statements in this column are true. None of them. So we should have had 0, 0, 0, 0 here, and we didn't. And there's really not been very much change over the 15 years. And I won't ask you to give all your answers, but my guess is that a fair proportion of this audience would have also believed that at least some of these questions, some of these statements on the left were true. This is briefly why those results are not true. I've given at the top the definition of the p-value. And I've summarized how you can remember that result by firstly remembering that statistics does not prove anything. So anything which says, as it does here, H0 is absolutely disproved, H1 is absolutely disproved, cannot be the case. Statistics does not prove anything. The more difficult thing perhaps is that a significance test does not yield a probability of a hypothesis, but of the observed data. And that's given indeed in the definition of the p-value under the null hypothesis significant testing definition. It's the probability of the observed data, not of the hypothesis. This is a hard concept, as I think you should now be beginning to realize. And it's clear that it's still not the case. And I'm now going to move forward a few years to 2019. This is a short paper in Nature where a group of statisticians were looking across how people had interpreted results. And an analysis of 791 articles across 5 journals found that around half assumed that non-significance means no effect. A sort of basic error in the interpretation of statistical results. And secondly, that studies currently dubbed significant and statistically non-significant need not be contradictory. And that's because of inability to appreciate the power of a study. And this is illustrated in the figure here, where the horizontal line represents the significance of the study. An underpowered study will have a very large estimate, which may overlap with 0. But come up with exactly the same actual estimate of the effect. So these two studies don't actually contradict each other. It's just this is non-significant because it's underpowered, a point that we covered a little earlier. So we have this problem. It's been persistent in the literature. These are difficult concepts. What could we do? What could we do to improve situations? And I'm going to suggest a number of things that I think you, my audience, and perhaps me as an educator should do. And the first is clearly just to teach, as I am trying to do now, to try and give you some idea of the complexity of the concepts and make you think about them. And I've already told you, I think, a couple of these issues. The first is that not all p-values are the same. A p-value of less than 0.05 does not necessarily mean the result is significant at a 5% significance threshold. And I've given you this complicated definition of a p-value, the probability of the observed data or more extreme data points, given that the null hypothesis is true. But I've also, throughout this talk, emphasized how education is not enough. We've been telling people this for a large number of years, and it still is not getting through. And that's why I think a second approach is probably called for. And as a very radical alternative to this is simply to give up on significance altogether. And if you think I'm joking about this, well, this is the paper I just showed you in Nature. About 800 signatories have called for an end to statistical significance. Don't report something with a p-value less than 0.05. Do something else. Well, what would that something else be? This group of statisticians suggested that we should be more nuanced. We should describe the results, put them into some broader context. I'll give you their wording. Authors will not rely on significant tests. When p-values are reported, they will be given with a sensible precision, so give the value, without adornments such as stars or letters to denote statistical significance, and don't give them as a binary inequality. It's less than 0.05 or greater than 0.05. Decisions to interpret or to publish will not be based on statistical thresholds. Well, of course, that's in the hands of the editors of journals who may or may not be listening to us, and we are largely beholden to them. And then the authors gave one last recommendation, and I wish this were true. People will spend less time with statistical software and more time thinking. Idealistic? Maybe, but it's certainly worth bearing in mind. And then there's one last way I think that we can deal with this problem, and I'll summarize it, if you will forgive me, with reference to the cultural North Star, which is don't believe your findings, be cruel to your data, and wherever you can, torture your analyst. And maybe if you just follow those three rules, we'll end up with findings that we're more ready to believe in when they get into the literature. Finally, just relying on statistical significance, repeating experiments is not enough. And I'd refer you to this paper where my friend Marcus Manufo, together with George Davies Smith, were arguing that we need to have disparate lines of evidence, not just statistical, not just repetition, in order really for allow us to put the results into, let's just call it common sense. If we see something and it doesn't make sense, but it's significant at a p-value of less than 0.05, then don't believe it. Do more stuff. Try and work out some way of interpreting that result. And for my very last slide, I'm coming back to a point that Dr. Gitlin made at the beginning of this talk. You can find more about this and more discussions and more examples of things that have gone wrong and things that have gone right in how genes influence behavior. So thank you for your attention, and I'll be happy to take some questions now.
Thank you, Jonathan. That was great, especially for a mostly clinical audience. So there are a number of questions, and I have my own. Let me go back and forth between statistical questions that are coming from people who obviously have done research and struggled with these issues, and more clinical questions. So one question is, what are your thoughts on Jacob Cohen's recommendation to replace p-values with effect sizes and confidence intervals?
That is the suggestion that I put forward at the end of my talk, and indeed it's a reasonable approach. Just give the effect sizes and the confidence intervals. Of course, we hit this problem that publishing it requires us to get the editors of journals on our side. So there's a big cultural problem with that. I think theoretically it's a great idea, but we have cultural problems here. They're not just questions of analysis.
As you say about the culture issue, one of the thoughts that I had listening to you was, it would seem to me that probably all major psychiatric research journals have statistical consultants available. And if they do, why is it there are so many papers that still get published that are unreplicated because the design or the statistical analysis was simply interpreted incorrectly?
I think a number of reasons for that. The first one I'd appeal to is the one I showed you in that study of how well statisticians themselves understand the null hypothesis significance testing. So even amongst that group, not everyone got that test right. So strictly speaking, it's a very hard problem that we're facing just in understanding what a p-value is and how to apply it. So I think you need a pretty sophisticated person running your journal to really pick up the errors that are getting through. That's not to say that they don't stop some things, but it's clear that's not enough of a bulwark, and it's partly because of their own background and training that's going to be an issue. The second problem we face is that statisticians are typically brought in after the experiment has been carried out. It's a bit like that quote I gave from that poor statistician who was dumped on by a lot of researchers saying they want to do good stuff, they've done some studies and got some results, and they just asked me to make it significant. Then people are not involved from the very beginning in the design and the interpretation of the data. And again, think of Richard Feynman's problem. I mean, the guy comes up to him and says, make it significant, make it significant. I've done the experiment. That's not the way to do it.
Was there any response, as an example, to that paper by 800 folks that said, we need a different way of publishing?
Yeah, tons of response. Twitter sphere breaks up into excitement, and lots of people sort of publish their own views, but it hasn't changed anything. It's at least got to the stage where the question is being discussed. So I wouldn't say that the needle hasn't moved, but in terms of getting journals to change, actually there is one thing here. So that actually it might be worth. This is probably, I should do a separate talk on this. There's a big problem about journals per se, the whole thing about publishing, and that breaks down into a number of elements, one of which is the reviewing process. Are we reviewing in an efficient and effective way? So if you could get reviewers to accept that you didn't have to p-value less than 0.05, you change things. So I work with eLife, and there's been a lot of conversation amongst the editors there as to the way ahead. And they decided that what we should start doing is publishing all the reviews. So, and we did a little experiment where what we did was we took a paper, and before it was reviewed, we made a decision whether it was going to be published or not. And then we published it with the reviews. And we said this to the authors. You can go for this. We're running it as a sort of test. We're going to make an editorial decision whether we publish it or not. So we suspected a bit of a higher bar, but these are editors. You know what editors are like. They've never got time to read the paper fully. So it's, you're sort of prejudiced against rejecting it, prejudiced towards rejecting it. And then those that we thought we were going to get, we liked, we sent out for review. And there was a bit of backwards and forwardsing around that. No, we didn't come to a sort of, I think, full, it wasn't, that experiment was a little mixed in its results, and it didn't resolve things completely, but it's an indication that people are beginning to ask these questions and beginning to deal with the culture. So I suspect if I give this talk in 5 or 10 years' time, we'll have a rather different environment in which we're dealing with things.
Great. Another question is, in your meta-analysis of the gene by environment on depression, is it possible that the interaction is dependent on certain kinds of environments, such as early childhood abuse? Maybe those studies mix or conflate life events with childhood adversity.
That's exactly the sort of issues that kept that debate going for more than 15 years. And that is why that paper now has, the original paper has more than 10,000 citations, as all of those objections were raised. Each one was beaten back, well, at least the authors of the rebuttal papers believed, only for someone to come up with another objection to it. It's a really hard problem. And I think the answer is probably not in querying the design of that paper so much as going back and saying, well, look, if we want to answer this question, let's design a study that could answer it once and for all. And indeed, a group did that, and they said, well, we really would like to make the ideal paper to address this, given what we know about the power and so on. That was published 2015, I think. And of course, there were a whole set of complaints about that one too. There's a type of evidence which you cannot get rid of. It's called vampirical evidence. It rises from the dead, however deeply you stick a stake through its heart. Now, how you deal with this problem, I don't know, but the question is perfectly valid, and I don't have an answer to it.
Okay, thank you. Another question from one of my colleagues is, I would think that habitually using a large N and always saving half as a validation sample would manage most false positives, regardless of whether you use effect sizes or p-values, presuming that the statistics are planned in advance and not hacked.
So the answer to that question will depend on the power that you want, with which you're powering your study. What effect size do you expect to detect? What is large for one study will not be large for another. This was the problem that affected genetics for 20 years or so, that people thought 1,000 was a large sample size. It now turns out that for some studies, 100,000 is probably the appropriate size. If you know the effect you're looking for, then what you say is true. If you don't know the effect size or do not have a good estimate of it, then you're up shit creek.
Well said. Another question from one of my colleagues: how do we address statistical complexity in the era of big data, since often we're no longer using straightforward t-tests and ANOVAs that we already struggle with in the scientific community?
Well, as you know or may know, that the short answer to that is to go to somebody who will peddle you something called artificial intelligence or machine learning, which is essentially throwing up your hands and giving up on standard statistical testing altogether. And there's some value in that, though, of course, our problem is trying to interpret those results, and it certainly won't give us a meaningful outcome. I sort of, before one gets there, I think, and I didn't go through this because the mathematics is so horrible, is getting into Bayesian statistics. So there are sort of halfway houses along that route, but that's a second lecture, I think.
Okay. Rarely in GWAS studies, including integrative studies, are epistatic effects mentioned, and can current analytic models adequately estimate these effects, which are likely involved in complex neuropsychiatric phenotypes?
Well, I would have to object. There is, from any GWAS, any evidence of epistatic effects. The only one I know is from a study of an immune phenotype. I think it's, what is that, B52? Blast it. There's a thing that gives you a bad, people suffer from bad backs and things. I'm blessed if I can remember at the moment. But the evidence for epistatic effects is, I'm afraid, really, really minimal. So I think that's one of those things you can chase for a very long time and very unlikely to find much evidence forward. And indeed, on theoretical grounds, we wouldn't expect that, because what we're dealing with in genome-wide association studies are common variants, and from quantitative genetic theory would expect that additive variance dominates to a huge extent. So if they're there, they're going to be really tiny.
Two value-laden questions. One, do you think the institution of tenure underlies this push to publish no matter what? Would you care to comment on that?
Question. That's a very interesting question. I have looked at what are so to reformulate that question, what are the factors that would lead to people publishing p-values less than 0.05? And you can do this by taking things like where things were published, the date of publication, the author lists, and so on. And ideally, I think it would be interesting to do it by where in someone's career they were. So do people who are an associate or assistant professor, are they more likely to publish studies less than p-values less than 0.05? My guess is you're probably right, but that's a testable hypothesis. It'll be interesting to try and do that.
And the last question, just because we don't have time for more, is would it be helpful, this is a perfect segue, Do you think publishing studies that are not significant would add to better interpretation and a fuller view of really
Yes.
all the data?
Yeah, absolutely. And the journals have done this. There's been some realization, particularly for significant findings that have attracted a lot of interest. It has been, it's becoming more reasonable to submit and publish in relatively high profile journals non-significant findings if you can convince the editor that to do so would make a difference to the field. So yes is the short answer.
Excellent. There are still 1 or 2 questions. I will send them. We can send them to Dr. Flint to answer, but we've gotten through most of them. Thank you, Jonathan, of course, for this erudite discussion on what is usually a rather dry topic.
Indeed.
So appreciate it. Thank you all for joining us, and we look forward to seeing you again next week.
Thank you for the stimulating questions. Actually, that's made me think of a few things. I will
Excellent.
change my talk as a consequence. Thank you very much.
Bye-bye, everybody.
Bye.